So let's do problem number 9 on page 787. And here is what's given. I'll read the problem. It says, a uniform electric field of magnitude 325 volts per meter is directed in the negative y direction, as shown in figure 25.9, which I've reproduced right here. The coordinates are A are negative 0.2 and negative 0.3 meters, and those B are 0.4 and 0.5 meters. Calculate the potential difference B minus A using the blue path. Okay, well, you can do that. Sure, we can use the blue path to do that. And see, if we go, well, here's where I always start, okay? And this is my approach to problems. I start off with the basic equation for voltage. A change in voltage is equal to negative E dot dr, or ds. Sometimes people use ds instead of dr, and that's just perfectly fine. This is a displacement. The electric field times displacement gives us the change in voltage. Okay, well, what I'm going to do here is break this up into two pieces, from here to here and here to here. And this is a dot product, by the way. So delta V is going to be, well, let's go from here to here first. First of all, the electric field is a constant in this problem. So we can say, well, this is a constant, so it's just negative E dot delta R. Okay? That makes sense? This, when you integrate, you have a constant. You can bring that constant out, and just the sum of all the little dr's, when you add up all the little dr's, you just get delta R. That's what that means. So, but we want to go on this path, so we're going to go from here to here. So this is going to be negative E dot, and we'll call this delta R1 plus negative E dot delta R2. And so this would be delta R1 and delta R2. You didn't have to do it this way. It's just the way I'm doing it. But see, this is a sum, so you can break it up and then add those things together. That's what, integration is the sum of all these little products. So here we've broken, instead of an infinite number of products that we're adding up 2 products, which is a lot easier. All right, so now delta V is equal, let's go this. This is negative 325 volts per meter times, well, what is delta R1? Well, you're going in an upward direction. Oh, first of all, I got to put a direction on this. This is in the negative j hat direction, this electric field. Right, so negative j hat. And that negative here, it's already there. So yeah, these negatives are going to cancel here in a second. Then dotted with delta R. Well, this delta R going from here to here is, well, let's see. It's really just changing the y value, right? So it's going to be 0.5 minus negative 0.3, or 0.8 meters in the j hat direction. Do you see that? Okay. Going from here to here. You could go, okay, it's y final minus y initial, and y final is 0.5 minus y initial, which was negative 0.3 meters. And so when you 0.5 minus negative 0.3 is 0.8 meters. But it's pretty obvious when you draw a picture of it. Well, 0.8. I didn't draw this to scale very nicely, but oh well. So this negative goes away. And so for our first part, that's going to be, well, let's go ahead and add the second one, since it's going to go away. Do you realize it's going to go away? That we're not adding any voltage, or we're not changing our voltage when we move across from here to here. because, and I'll show you why. It's negative 325 volts per meter in the negative j hat direction, dotted with, well, what is this is delta x. Well, what is delta x here? It's 0.4 minus negative 0.2, so that's 0.6 meters, but that's in the I hat direction, isn't it? And what do you get when you go j dot I? You get 0. But a way of looking at, okay, that's the mathy way of looking at it, which is just fine. But look at it from in a physicsy way. Now I drew the electric field down here, but it was stated in the problem that the electric field is basically everywhere, right? So and so when you go across like this, you're going across the electric field. You're not doing any work against that electric field, so you're not gaining or losing any potential. It's like walking on a level floor. You're not changing your gravitational potential, right? You're not gaining or losing elevation. Well, here we're not gaining or losing elevation within that electric field. That's kind of a way of looking at it. So this is it right here. So delta V is going to be equal to 325 times 0.8, which I believe you get 260. It's positive, and a volt per meter times a meter is a volt. So there you go. And that's the answer. So pretty, I made it a little bit more work by being a little bit more thorough than I would have been if I was doing this on homework, but that is how that's done. Yes?
Isn't this supposed to be the voltage of B minus the voltage of A? You did the voltage of A minus the voltage of B.
Well,
does that matter?
If this B, right, see the way this is written right here? And the question is, didn't I do B minus A? I mean, should it be negative 260 volts or something like that? Well, here's the way to look at it. This is my B here is my final destination. So A is where I'm starting. So think about this. If I'm going to move a positive test charge through this electric field, I gotta put work into it, at least to get it up here. So it's gained voltage, and then I move it over here, no change in voltage. And hey, this stuff is a lot easier if you visualize it and think about it in those terms. Okay? Like, what would a positive test charge do? Okay, I want to get a little wristband that says that, what would a positive test charge do? There. Okay. So,
Yeah, that should be the AP Physics shirt.
Oh, that would be a great AP Physics. Yeah, okay.
Positive test charge.
All right. Very good. That is all.